part B, the topic binary search and a selection problem. Yeah, these two topics, but our main topic is the binary search. Okay. Yeah. In our part A, after the insertion sort, I gave you two examples. In those two examples, actually, I already used the binary search idea. Yeah. So the binary search idea in our problem solving, very efficient, very important. Yeah. So today we learned the details. Yeah. So you know a little bit about binary search. Yeah. But we want to learn more details about binary search. B.1, binary search elimination. We understand why the binary search can solve the search problem so efficient. Yeah, the binary search. Later you will see in the real world applications, the binary search plays a very important role. Yeah. For example, in database management system, how to search a row satisfying certain condition very fast. Assuming you have a large number of rows, millions of rows, how can you find the row satisfying certain condition extremely fast? The main algorithm is the binary search. The main algorithm, the most important one, although it's not covering all the cases, but covering 90% of the cases. The binary search based algorithm, in database, DBMS system, internal, fast search. Main idea of the fast search is implemented by binary search. Yeah, so it's so important. Yeah. All right. Question number 12, search an ordered array. So here, the main difference. In our linear search, unordered array. Now, the most important thing is, because only when we have an ordered array, we can apply binary search. Otherwise, we cannot apply binary search. Yeah. But in the real world situations, it's very common. Many people, when they apply the binary search, they are not aware of their data should be ordered. They just apply anyway. Okay? Yeah, that happens a lot in the real world situation. Okay? Yeah. After we learn this class, you need to check if the data is ordered. Yeah. Otherwise, your result won't be correct. Yeah. All right. Given an ordered array, sorry. Yeah. And the search key V, question, how to find an index I such that V equals A or Y? That's our search problem. Yeah. But here, this ordered information, you need to use it to help you find the element in the fastest possible way. Yeah. All right, so here, I'll give you the reference in the textbook. Yeah. All right, the analysis, what's the idea? Basic idea, elimination method. We want to use this property, ordered data property, to help us eliminate as many elements as possible after we do each comparison. Yeah. We want to make our number of comparison, that number, the minimum. Yeah. The best solution, the minimum number comparison. That's the best solution. Yeah. So in order to get the best solution, after each comparison, we want to eliminate as many elements as possible. Then we can get the best solution. Yeah. All right. So now let me show you the idea. Reduce the problem size by the ordered data property. Yeah. after you do the elimination, your problem size is reduced. Yeah. Yeah. So let's look at how to reduce the problem size. Yeah. How can we take advantage of the ordered data property? Yeah. So that's the main consideration. Yeah. How can we take advantage of this property? Ordered data property. Yeah. Answer is very simple. Because when we have ordered data, we can make our prediction well. You need to make prediction, right? Yeah. Yeah. Now we can make good prediction. Yeah. Order the data. Yeah. All right. Explore the order property. Yeah. All right. Here, let me use a diagram. Yeah. Yeah. Our array is an ordered array. Yeah. Order. I like to draw, this arrow. So, it's an ordered order, ascending order. Yeah. Now, when we compare our V element, V key, let's treat it as a key, okay? V key, the value of elements, V key with, any element in the array, we have many different ways for the comparison, right? Yeah. Now, we need to think about what comparison would give us the best result. That's the question. Well, we have so many different options. So which option would result in the best overall result? Yeah, that's the question. Best overall result. Yeah. Okay? Yeah. Best case, worst case, right? Yeah. Okay? Best case, worst case. Yeah. You want to consider the worst case, not the best case, right? Yeah. You want to consider the worst case, not the best case. Yeah. Here you can see. Keep in mind, in order to get the best algorithm, we want to target the worst case situation. No. All right. No. Yeah. So you can do, all those different ways for your comparison. The question, after one comparison, how many elements can be eliminated? Yeah. All right. Yeah. So let's consider the elimination part after one comparison. So here, in order to simplify our situation a little bit, we like to assume our elements are distinct elements. This array, elements, distinct. Okay? Yeah. Simplify. Yeah. Later, after we can solve the problem later, we extend it to the general case. Yeah. But in our early discussion, we want to make our data as simple as possible. Yeah. So we assume, the elements, distinct values. Yeah. All right. Then, when you do one comparison, there are two cases. Yeah. So let's assume, two cases. Yeah. All right. The best case, when V greater than the value of the current element. That's the best case. V greater. Okay? V greater or equal to A sub n minus 1. Yeah. Because greater or equal, you're done, right? Yeah. If it's greater than, you cannot find V in the array because you get the result. Yeah. It does not exist. Okay? The key to be searched, it does not exist in the given array. That's your conclusion. If V equals, you find it, right? Yeah. So V greater or equal to A sub n minus 1. That's the best case. Yeah, you can make your conclusion. Yeah. Then other cases, worse than the best case. Yeah. V less than A sub n minus 1. Yeah, because V less than, you need to consider, all the remaining other cases. Yeah, you have a lot of work to do. Yeah, yeah. So here you can see you have best case, you have other cases. Yeah, yeah. But we are interested in the worst case, not the best case. All right, that means we want to consider this part, that part. Okay, all right. Yeah, so to understand, because here, when we make our selections, we want to use different angles to understand the situation. Yeah. So one way to understand, that well-known Murphy's law. Okay, Murphy's law. Yeah. So we are familiar with this Murphy's law. Yeah. So we can use one sentence to state it. Anything that can go wrong will go wrong, although something related to psychology or whatever thing. Yeah, but here the essence of this statement is the worst case, because anything that so we treat this as the worst case, right? That can go wrong. Yeah, yeah. So will go wrong. So that means we need to really seriously consider the worst case, right? Because we need to prepare for the things going wrong. Yeah, so we need to prepare for the worst case. Yeah, let's understand in this way. Okay, yeah, worst case. Yeah, yeah, yeah. Even based on the Murphy's law, the worst case is so important. Yeah. All right. Yeah. Yeah. So then next, so based on this, yeah, we think our main step. So this is our main step. Compare one right in the middle. So we have so many different options. Yeah, the best option is this. Compare this V with the element right in the middle. The middle. Okay. Yeah. Not too close to the left end. Not too close to the right end. Yeah. Yeah. It should be as close to the middle as possible. Yeah, yeah, yeah. So that's the key step. Yeah, yeah. All right. But how to understand the step? Why this comparison? Compare V with one in the middle. Yeah, with the one in the middle. We can call median. Yeah, because it's ordered array. The element in the middle in the ordered array, it's a median. Okay, so we compare V with the median. Yeah. So regarding the median, I want to clarify the concept a little bit. Yeah, because when I talk about the median concept, many people ask me, well, you have even number of elements, right? No problem. The median, we know, only one element in the middle. That's the median. But when you have even number of elements, yeah, when n is even. Because you have two elements, yeah, equally close to the midpoint, right? Equally close, yeah. So those two elements in the middle. So actually they are both medians, yeah. They're both medians. One is the left median. Another is the right median. Left and the right median. Two medians. Yeah. Left median and the right median. Okay? All right. But what's the definition of median? Yeah. So, yeah. But the definition of the median, there. Here, I want to clarify the definition of the median. Yeah. In math and computer science, the way to define a median could be different. Yeah. So now we use the computer science definition. We do not use the math definition. Okay? Yeah. Because the math, if you use the middle school, yeah, in the middle school, if you can recall, middle school, the median in this situation, you have left and the right, then sometimes people define this way: average of these two numbers, treat as the median. Okay, average. Yeah, that's the math way. Yeah, we don't use the math way. Our way. Yeah, default median. Yeah, because if people do not say left median, right median, just median. Median, that means the default median. Default median is the left median. Okay. Left median is the default. If people just say median, that way, for the even, n is even number, left median. Okay? Yeah, yeah. Here you can see, in our computer science, we define this way. It's better than the math way. The reason the math way, if you take average of these two median, then your median is not one of the elements in the array, right? It's different from any element in the array. Okay? Then it's not good. In our computer science, our median must be one of the elements in the array. Because we need that. Many of our algorithms, we need to find the median element. We need to take that element out. That's important. So in math, it's different, right? So in math, so they don't need that. They just want to find a midpoint. Okay? Yeah, it's different from. So our goal, because we need to use that median element, one of the elements in the original array. Okay? Yeah. Yeah. So we need to use our computer science definition. Yeah. All right. Now, so here we say the best way compare V with the median element. Yeah. Because in this way, can we achieve our goal here? Achieve our goal here, so we can eliminate as many elements as possible. Yeah, so our goal, eliminate the maximum number of elements after one comparison. That's our goal. Okay? After one comparison, we want to eliminate the maximum number of elements in the array. Okay? Yeah? Do you feel if you choose the median as the first comparison, you can achieve this goal? That's the key step we want to understand. Yeah. Okay. All right. Yeah. So here I want to explain this point. Okay. Yeah. This point. Okay. Yeah. 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 So here there is another view on this step. Yeah. So we call it balancing principle. Yeah. Yeah. So what's the this balancing principle? Yeah. You treat your whole array as data, right? Yeah. The balancing principle is because you need to make a decision to split your data into two halves. Yeah. When you compare one in the middle, you split, right? You compare the key with any element in the way, you split already into two parts, two subarrays. When you split your data into two parts, the balancing principle tells us the most efficient way is you split with a balanced way, in a very balanced way. Okay? Yeah. If it's an unbalanced way, yeah. So one subarray, the size very small. Another subarray, the size is very large. Usually, the more unbalanced the split you do, the slower your algorithm. Okay? The more balanced the way you distribute your data, the faster your algorithm. Yeah, so that's this balancing principle. Okay, so that's one way. Yeah, so we should split right in the middle. Yeah, because that's the most balanced split. Okay? Yeah, so that one corresponds to the fastest performance. Yeah, so that's another view of this, the split. Yeah. Okay. All right. Next, I want to talk about efficiency analysis of binary search. Yeah. But for this efficiency analysis, now we need to count the number of comparisons. Okay, number of comparisons. Before we do that counting, I want to introduce another important view. So why split in the middle is the best. We have another interesting view. I want to introduce to you because this view is also very useful in problem solving. Yeah. So all right. So that important view is called adversary argument. Adversary argument. Adversary argument. This adversary argument, why we use that? So the main goal we use the adversary argument is help us to handle the worst case. Worst case. Because when we solve a computing problem, we target the worst case. All right. So here, let me explain how do we apply this adversary argument to help us address the worst case. Here, the idea is like this. We imagine, so there is a very smart adversary fighting against us. Because it's our adversary. We want to beat this adversary, right? We want to beat it. But the adversary is very smart. Okay? So the goal of the adversary to give us hard time, right? Try to make the problem as hard as possible, right? The adversary, the goal is to make our lives harder and not easier, right? That's the typical job, from the adversary. All right. The adversary will always feed us the worst case. That's the logic. Okay? The adversary won't give us the best case, right? That's too easy. The adversary always try very hard to feed us the worst case. In every move, we ask our adversary. Because when we do comparison, there are two results, right? Greater than V, less than V. Okay, those two cases. These two cases, we should not select these two cases by ourselves. Because if we are allowed to select from those two cases, we will select easier case for us, right? Because then we can do faster. So here, we should not select by ourselves. We should ask our adversary, which case you want to give us? The adversary will pick the worst one. The adversary won't pick the better one for you, right? The adversary will pick the worst one for you. That's the adversary argument. Here, let me explain. Suppose we have this ordered array. All right. All right. So when we do comparison, suppose this is our key V. Comparison. Okay. All right. You can determine the first comparison. That's your decision. You can make your decision to compare V with any element in the array. Okay. You can choose anyone you like to do the comparison. Okay? Yeah, the first comparison. When you do function comparison, let's, for example, we compare with element here. Okay? Yeah. After comparison, then there are two cases, right? First one, V falls into the first subarray. That's the first case. Okay? Case one. Yeah. The second case, V falls into the second subarray. Okay? Yeah. One longer, one shorter. Okay? Yeah. All right. Then, when we make a decision, we ask our adversary, okay, which of the two cases you want to give us. Okay? Yeah. So then, which one do you think adversary would give us? Case one, case two? Case two. Yeah. Because case two longer, right? Yeah. The size of the subarray is larger. Then you need to do more work, right? When you work on the data size with larger size, you need to do more work. The data size with shorter subarray, you need to do less work. And the goal of the adversary is forcing us to do more work. That's a good adversary. Okay? Forcing us to do more work. Yeah. So the adversary would pick the longer subarray for us to work. Okay? So adversary told us V falls into subarray number 2. Now you need to work on that longer subarray. Okay? Yeah. Yeah, that makes sense, right? All right. Now, based on this understanding, yeah, because we fight against our adversary, we need to make our strategy to beat the adversary, right? Yeah. So we don't want to surrender, right? We want to beat our adversary. Yeah. So we need to make our smart strategy to fight against our adversary. Yeah. All right. Now we are here. Ordered array. This time, we modify our strategy. Okay? Yeah. Because in order to beat the adversary, we modify our strategy. We have V element, so we pick the midpoint. Okay? The midpoint. Yeah. Median. Yeah. Right. We compare V with this midpoint. Okay? All right. Then case 1, case 2. Okay? Case 1, case 2. V could be in case 1, could be in case 2. Yeah. This time, because we choose the midpoint, the size of the two subproblems the same. Okay? Same. Now we ask adversary. So which case you want to give us? The adversary could choose case 1 or case 2, but the same difficulty, right? Yeah? The amount of work for case 1 and case 2, the same amount of work. So in this way, no matter which case the adversary chooses, yeah, no difference. No difference. Okay? Yeah. So in this way, so we design our strategy. So when we fight against this adversary, after we let the adversary tell us which subarray to choose, do we get the best we can get? Right? Yeah. Because in this way, we only work on the problem of half the original size, right? Half the original size. Yeah. But if the data is not evenly distributed, okay, one longer, one shorter, but the adversary forces us to do work on this one. Is it greater than 1/2 of the size? Yeah. So, as a conclusion, if you do not do the even split, the adversary will always let us to work on the problem size that's greater than 1/2 of the original problem size, right? Greater than 1/2 of the original. But if we choose the midpoint, then that's the best we can get from the adversary, right? Because equals 1/2 of the size. That's the best we can get from the adversary. So in this way, we can say we get the best decision. This is our best decision. Yeah. That's the adversary argument. Okay? Yeah. So later, when we solve some other problems, so there is a chance sometimes you need to consider this adversary argument. Yeah. To help you fight against the worst case. Yeah. All right? Yeah. So let's move to the efficiency part. Yeah. All right. Now we want to count the number of comparisons for the worst case. Yeah. So the whole problem size, the line segment, this long. Yeah. Now we assume the midpoint comparison, the median one. Okay. All right. After each comparison, what is the size reduction? The problem size reduction. 1/2, right? Yeah. So we can drop either left half or right half, but the remaining 1/2 of the size. Okay. Then the second comparison is still the median of the current array. So drop another half. Yeah. Every time we drop half of the problem size of the current array. Okay. We can keep doing. Keep doing like this. But the question is, when do you terminate? When do you terminate? Yeah. We need to know after how many number of comparisons. Then we get to the last step. We need to figure out. Okay? Yeah. So that's the next technical problem we need to solve. Yeah. Given original array size n elements, after we do certain number comparisons, yeah, that's the last one. No more comparison is needed. We need to know that number or that formula. Yeah. Yeah. Now let's calculate. All right. We look at the problem size. Okay, all right. Yeah. Original problem size is n. Original problem size n. Yeah. Yeah. After one comparison, the problem size becomes n/2. Right? We cut it in half. Half the problem size. After second comparison, another half. So the problem size becomes n/4. And so on. Okay? Every time divided by 2. Yeah. After k comparisons, n/2 to the kth. Yeah. So you do division by 2 k times. Yeah. n/2 to the k. Okay? All right. Yeah. Now you need to figure out which k corresponds to the last comparison. Which k? That means after you do k comparisons, you reach the very end. No more comparison is needed. We want to find that, describe that condition. Okay? Yeah. So that k, yeah. Yeah. That termination condition, we want to know that. Okay. All right. So let's try to, we want to use some inequality to describe the termination condition. Yeah. All right. Yeah. Stop splitting. Yeah. Then, if we look at the problem size, if the problem size is less than 1, yeah, less than 1, okay, yeah, yeah, here, yeah. Length less than 1, then it can cover at the most one element, right? Yeah, it cannot cover 2 elements, right? 2 element, yeah, yeah, because here we assume our elements distributed evenly, okay? Yeah, yeah. The difference between 2 elements, 1, 1, okay? Yeah. Yeah. Right. But now, if the problem size is less than 1, that small line segment can only cover one element, right? Yeah, less than 1. Yeah. If it covers one element, do you need one more split? You don't need no split needed, right? Yeah. So that's the end, okay? That's the end. The problem size, when the problem size is less than 1, no split is needed. Okay, yeah, okay, all right. Yeah. Yeah. That's one side description. Yeah, problem size less than 1, one side description. But you need another side, right? Because before the split, the previous split, you need to look at the previous split. Yeah. The previous split, you need to do a split, right? Yeah. The previous one, the size is greater or equal to 1. Then you can do another split, right? Because it's greater or equal to 1, it contains at least 2, it can contain 2 elements, right? Yeah. If it covers 2 elements, you need one more split, right? Yeah. Yes, you still need to do one more split. So the previous one, greater or equal to 1. Yeah. After the last split is strictly less than 1. But the data size after the previous split, greater or equal to 1. Okay? Yeah. All right. So in that way, yeah, this is the size after the previous split, right? Yeah. N over 2 to the k minus 1. Yeah. That's the data size after k minus 1 splits. That should be greater or equal to 1. And n over 2 to the k, that's after k splits. After k splits, the data should be strictly less than 1. Okay? This is our termination condition. Termination condition. This inequality is the termination condition. Okay? Yeah. Now we want to find a relationship between k and n. K and n. Yeah. Now we just solve an algebraic problem. Yeah. Relationship between k and n. Okay. All right. Yeah. Let us remove the common denominator. Okay. Yeah. So we get 2 to the k minus 1 less than or equal to n, strictly less than 2 to the k. That's inequality. Okay. Yeah. We can take log base 2, right? We can take log base 2. Yeah. If we take log base 2, k minus 1 less than or equal to log base 2 of n, strictly less than k. Yeah. That's inequality. Okay? Yeah. That's our termination condition. Okay? All right. Yeah. Then, yeah. What's next? Yeah. What's next? Yeah. Then, if you look at this current termination condition, still not very good. Why still not very good? Because look at this expression, log base 2 of n. Yeah. In general, this expression is not an integer, right? Log base 2 of n. Most of the cases, it's not an integer. Yeah. When n is not power of 2, this number is not an integer. Yeah. And k minus 1, k, they're both integers, but this one is not integer. So you compare a non-integer number with integer numbers. Although you can do that, but you have room to improve, right? You have room to improve. Yeah. So we want to convert this expression to integer expression. Yeah. Then we compare integer with integer. It's better, right? Yeah. Integer with integer, then because they could be equal. Okay, they could be equal. Yeah. Here, this side, although this side could be equal, but this side can never, strictly less than, right? Strictly less than, yeah. Never equal, never equal. Yeah. How about after our improvement, we can make this upper side equal, also equal. That is improvement. Yeah. Upper side also, we make it equal. Yeah, that's improvement. Yeah. All right? Yeah. So next we need to work on it. Okay? We need to improve this inequality. All right. Derive the worst case formula. Yeah. Worst case formula. Worst case, that means given n, you need to find k from n. Okay? You need to give me this k in terms of n formula for the worst case. What is the worst case formula? Okay? Yeah. Before you complete this topic, yeah. So here we still, yeah, I hope I can complete this topic today. Yeah, we have some time. Yeah. Before we complete this topic, yeah, if I ask you, yeah, given an array with n elements, we want to do binary search, ordered array with n elements. What is the worst case? When we apply the binary search, worst case. Do you have an idea? Yeah, because you, at this point, at least you know binary search a little bit, right? Yeah, you know a little bit binary search. Yeah, yeah. Given n element array, ordered array, what is the worst case? Do you have an idea? Approximately, at least you know approximately, right? Yeah. Let me give you concrete numbers. Give an array with 8 elements. 8 is the power of 2, right? 8 is the power of 2. That's easier, yeah? Because you can split. So you can divide it by 2 all the time. Yeah. Given an 8-element array, I'll ask you, we do binary search on it. How many comparisons you need? 8-element array, binary search. Number of comparison. 4, Matthew. Kiri? 3. Kiri 3, you 4. You are correct. He is correct. Yeah. If 7, it's 3. 8 has to be 4. You can think about it. Yeah. So Kiri here. Okay. You think about the element distribution. You have 1, 2, 3, 4, 5, 6, 7, 8. When we do comparison, the median, that's comparison with 4, right? First, yeah, yeah. Then our adversary will tell us the element should be in this larger subarray, right? 5, 6, 7, 8. Yeah. So the second comparison with this median, 6 element. Yeah. Then our adversary will tell us, you know, yeah, so after the second, it's in these 2 elements. Yeah. Then the third one, this is the third one. You do comparison with 7, but our adversary will tell us it's number 8. So our adversary forces us, we need to do 4 comparison to get it.
Will we know from the third comparison that it has to be 8?
Oh, you mean the fourth one we do not need to do? You need to make assumption. The key must appear in the array. But you cannot assume that, right? The key is not necessary in the array. So you have to do the last comparison. Yeah? Yeah. Yeah, see? Here you can see, if you apply the adversary argument, you can get the worst case. 4 comparisons, not 3. So you are right. Good sense. Yeah. Good intuition. Yeah. 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 Because, why I ask you this question? Because people, when they answer this question here, 8 is equals 2 to the third power of 2. People tend to apply log base 2 to get the answer. Okay? Yeah? Because binary search, you look at here, log base 2. Then people just select, apply log base 2. Then you get a wrong answer. Yeah. Not accurate, okay? Not very accurate. Because if I ask you, when you have an array with power of 2, 1024, that is 2 to the 10th. Yeah. That's a power of 2. Okay? If I ask, you apply the binary search, what is the worst case? How many comparisons do you need for the worst case? 11. 11. Not 10. Okay? One more than 10. Okay? One more than 10. Yeah. When you have power of 2. Yeah. All right? Yeah. Yeah. One more than that exponent number. Okay? If it's a power of 2. Yeah. But people tend to use that exponent number. Yeah. Okay? Most people. Okay? Yeah. You are in the minority. Yeah. 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 All right. Yeah. Yeah. But here we need to get the formula. Okay? Definitely, if you use the floor function, that's not correct, right? Yeah. Because in order to convert this formula to integer expression, we have floor function or ceiling function. If you use floor function, it's not correct, right? Yeah. If you use ceiling function, still not correct, right? Yeah. Because when n is power of 2, ceiling function is the same number, right? Yeah. So ceiling function, floor function is incorrect. Yeah. That's why right now we want to figure out the correct formula. What is the correct formula for the worst case binary search? Yeah. So we need to do some work. Yeah. We start with, when we start, yeah, so here, because this condition, we can write it as this inequality. Yeah. 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 All right. All right. This side equal, that's good. Okay. Yeah. Yeah. That means k could be equal to, yeah. Because k is an integer equal, when we put the floor function, also correct, right? Yeah. Floor function. Yeah. Also correct. Yeah. 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 All right. So we're satisfied with this side. But how about that side? We're not satisfied with that side. Yeah. It's unequal. It's unequal. So we are not satisfied. Okay? Yeah. All right. To make the lower side equal, we need to do some tweaking. Yeah. Do some tweaking. Okay? All right. Let's do the tweaking here. Okay? We go back to this is our original inequality. Yeah. So we do tweaking in our original problem. How do we improve this place? And strictly less than 2 to the kth power. How do we improve that? We want to improve slightly. Any idea we can improve? Improve means we want to achieve that equality. Yeah. Here, no equality. Never happens. The equality never happens. But we want to improve it to make equality could happen. That's the case. Equality could happen. Okay? All right. Yeah. The way is we add one more. Yeah. We know n is strictly ln power of 2. Both integers, right? N integer, power of 2 integer. 2 integers, but one is greater than the other. Okay? Can we add one more to the smaller integer such that n plus 1 less than or equal to the larger one, 2 to the kth? Yeah? Two different integers, their gap at least 1, right? We know there are two different integers. One is greater than the other. The difference is at least 1, right? Now we raise the smaller one by one more. Can we make greater or equal? Can we make the equality possible? Yeah. After we increase the smaller number by 1, we can make this equality as, inequality as equality, right? Containing the equality. That's improvement, right? Yeah. That is improvement. Okay, all right. Then, let's take a natural log. This time, we take log base 2 on m plus 1. So we get log base 2 of m plus 1 less than or equal to k. Then, the upper part, we keep it. We keep the origin, the old upper part. Yeah. All right? Yeah. The upper part, because there is that equal sign, if we take floor function, still true, right? Still true. The lower part, this time, it contains equal sign, okay? Yeah, it's a good improvement. Contains equal sign. Then we make a seeding function still true, right? Yeah. Yeah. Because after we make seeding function, we get an integer expression, okay? So we make seeding function going up, still true, okay? Yeah. In that way, you can see, our conclusion, we get 2 formulas. One from upper side, one from lower side. Okay? The first formula, K max, maximum number of comparisons. Max, the worst case. Yeah. That's the worst case. K max equals the ceiling function of log base 2 of n plus 1. n plus 1. Okay? Second formula, the K max equals 1 plus floor function of log base 2 of n. Both integer expressions, and these 2 formulas, they are in different forms, but they are the same. They are the same. Yeah. And we can prove it. Yeah. We can prove it. These 2 formulas always give the same result. Yeah. But here we skip that proof. The proof we need to use mathematical induction. Mathematical induction. Yeah. We need to do a lot of work to prove. Yeah. So here I skip it. Yeah. All right. And then this formula is given in our textbook, the appendix of our textbook. So this formula is given. All right, yeah. You can use either one, yeah. You can use either one. If I ask you to give us the worst case, given n, worst case, you just choose one of the 2 formulas. You can calculate the worst case. Yeah. All right, yeah. All right, then, so we just find the worst case. The best case. Best case always 1, right? Yeah. After 1 comparison, you hit it. Yeah, you're very lucky. The best case it could happen, V equals the median. All right, that's the best case. 1 comparison, you're done. Yeah. Hit it. Okay, all right. Yeah. Next question. After we get the best case, we get a worst case. The next question, average case. How to calculate the average case? Okay, that's another important question. How to calculate average case? Yeah. So the average case, you need to consider. Yeah. So all the possible cases, then you take average. Yeah. Here, in this topic, how to calculate the average, it's an important question we need to answer. Yeah. In this topic. Before we get there, so we use this topic to help us understand the average case better. Yeah, because average case, many people couldn't understand the average case well. How to take the average? How to take the average? Right? Yeah. In our module 1, we did once. In our module 1, linear search, we did that average formula, right? Yeah. In that one, our understanding of the average is the weighted average. Weighted average. See? Probability as the weight, right? Module 1, linear search. Probability P. P and the 1 minus P, two weights. Then we take the weighted average to calculate average case. Yeah. Here we have another serious situation. We need to calculate the average case. Yeah. Before we do that calculation, I will show you a simple example to calculate the average case efficiency. Before we get there, today we do not have time to calculate, so we leave that calculation next time. But today I want to do some preparation. We have 10 minutes. I need to complete my comments, within 10 minutes. All right. Now, use your current understanding of the average case. Your current understanding. So here we have our best case is 1, worst case this much. Two numbers. Now I want to ask you, can we calculate the average case by adding these two numbers divided by 2? Do you feel this way reasonable? You do not agree? How about Matthew? How do you feel? Can we calculate? Simple way, this is the average. Can we do that, this kind of calculation? Matthew? Kadi? Looks fine, right? It looks fine. Yeah. But Kirill, you said no. So can you say something? Why you said no?
Last time we did this, it didn't work.
Oh.
This time we calculated the average.
Yeah.
We also summed the best and the worst and divided by 2, but it wasn't the answer.
Yeah. Sometimes it works, sometimes it doesn't work. Yeah. So you should be very careful. Sometimes it works. For example, insertion sort, it works. Insertion sort, when we take average, the best insertion step and the worst case, the average case divided by 2. Insertion sort, it works. But here, binary search, it doesn't work. Yeah. Why? I explain. Yeah. Because the insertion sort, this is the best case, 1, okay? This is the worst case, they're high, okay? Between best case, worst case, all the other cases distributed linearly. So it's a linear function, okay? It's a line. Line, the average you take in the middle. That's correct, okay? And why binary search, it doesn't work. It's not a linear case, all right? The best case, what's the best case? Best case only 1 point, all right? Median, median. All right. Then you draw binary tree, okay? 2 comparison, there are 2 points you need to do. 1 comparison, you need to do only 1 point. 2 comparison, there are 2. 3 comparison, there are 4. You can see the number is not the same, okay? Yeah. All right? Because for the linear case, 1 comparison you have 1. 2 comparison you also have 1. So 1 comparison you have 1. 2 comparison you have 1. 3 comparison also you have 1. For each comparison you have 1. That's the linear case, okay? Yeah. But here, 1 comparison you have 1. 2 comparison you have 2. Okay. 3 comparison you have 4. Okay. Yeah. Every 1 more comparison you double. Okay. So you have this binary tree. Yeah. If you take average in this binary tree, how can you use this linear case formula to calculate? You cannot use the linear case formula, right? Because here, let me look at the time. I'll just say, I use 3 more minutes to complete this. All right. When you take average, do you need to consider the contribution from all levels, top level, second level, third level, bottom level? Which level has more contribution? To bottom. Yeah. So many points. The more points you have, the more contribution. Okay? The top level, smallest contribution. Do you need to do weighted average? The weight, the bottom should have the largest weight, the bottom level, largest weight. Second largest, third largest. So each level, the weights different. You need to choose appropriate weights for individual levels. Then you combine all the levels to get an average case. Then the contribution is different. That's why your formula, you cannot use the linear case formula. Okay? You cannot use the linear case formula, right? Yeah. That's the understanding of the average case. You need to look at the contribution. Okay? From different cases, contribution to the average case. Yeah. That's why sometimes it works, sometimes it doesn't work. Yeah. Because your data distribution is different. Okay? The data distribution, this linear distribution, it works. Nonlinear, this is nonlinear distribution. Okay? Nonlinear distribution, it doesn't work. Okay? Yeah. All right, yeah. So let me stop right here. Yeah. Next time we do the concrete calculation. Okay? We draw the tree, we plug in the numbers, we find the average case answer. Yeah. All right.